So another thing you have to understand about complex tones is the concept of a fundamental frequency. So every or most sets of complex tones have a basic frequency that all of the other frequencies in that tone start from. So, for example, a voice might have a frequency of, say, 10 kilohertz. And that fundamental frequency is referred to as the first harmonic. And then the second and third harmonic is a multiple of the first. So if my first harmonic is 10 kilohertz, then my second harmonic will be 20 kilohertz, my third harmonic will be 30 kilohertz, etc. Most of the complex tones that you hear have these harmonics. So you'll hear, for example, a violin string, for example, vibrating, and if it's vibrating at 10 kilohertz, it's not going to be a pure tone of 10 kilohertz, because you're also going to be you're going to hear the first harmonic of 10 kilohertz, of course, but it's also going to be generating the second harmonic, which is going to be 20 kilohertz, all the way up to 30 kilohertz, etc. So periodic complex tones consist of the fundamental frequency that you're hearing, as well as the harmonics that are multiples of the fundamental frequency. This is true for voices, musical instruments, anything. And this is why you can have, like, for example, a singer with a low voice and a singer with a high voice singing together in pitch, because what they're doing is they're just adjusting their voices so that they're using the same fundamental frequency. So if I have a fundamental frequency in my voice of 4 kilohertz, and then I'm singing with somebody who has a fundamental frequency of 7 kilohertz, we can adjust our pitches going up to the next fundamental frequency. So if I would go from 4 to 8, and the other singer would go from 7 to 14. When I go from 4 to 8 and he or she goes to 7 to 14, that's going to be perceived as being in pitch, because we are shifting together from our first fundamental frequency to our second harmonic. Additive synthesis is the process of adding harmonics to create complex sounds. And of course, this is a fundamental aspect of creating music, of creating musical instruments, creating, for example, the creation of violins. If there's a very expensive violin that's known as a Stradivarius violin, and people cherish these things. They're handmade, and one of the reasons they're so expensive is because they have just the right combination of craftsmanship and materials to produce beautiful mix of harmonics. And of course, we can do additive synthesis nowadays with computers and machines. We can mix different harmonics to create different sounds. Any complex tone, like my voice, for example, or a concert from an orchestra, or a symphony orchestra, the sounds from a symphony orchestra, is going to produce a very complex spectrum of sounds, and we refer to this as a frequency spectrum. And you can actually display a frequency spectrum from a source, such as a voice or a musical instrument. So, for example, here we would have this complex sound, and it might be, let's say, for example, a guitar string or a guitar playing, and this wave is actually going to be made up of 4 separate waves added together. It's going to be this wave, which is at 200 hertz, this wave at 400, this wave at 600, and this wave at 800. Notice these are the harmonics, right? So the primary frequency so this would be the first harmonic, the fundamental frequency, and then the second harmonic, the third harmonic, and the fourth harmonic, 200, 400, 600, 800. Notice that the harmonics are multiples of each other and multiples of the first harmonic. They all add together to create this waveform right here. And again, this might be like a violin string vibrating or a guitar string vibrating, for example, or a note being played on a flute. So here we have another example with where what we've done is we've taken the wave that we saw before with the the fundamental frequency, the second, third, and fourth harmonic, and then what we did was we took out the fundamental frequency. We took that out and just left in the three harmonics, 400, 600, 800. And one of the really interesting things about doing this is that the pitch doesn't change. It sounds different, a bit different, but the pitch stays the same. And this pitch that we get from removing the first harmonic, or one of the harmonics, is called the periodicity pitch. It's a very interesting effect that the fact that we can do this, we can remove the the fundamental frequency, in this case number 1, and be left with 2, 3, and 4, and we're still hearing the same pitch, referred to as the periodicity pitch. And one more thing about periodicity pitch is that we experience it all the time. Whenever you listen to somebody talking on the phone, they sound different than when you're talking to them in real life, but you still can tell if it's a male or a female, and you can still tell usually who it is. That's because the microphone in the phone and the transmission of voices in phones removes a lot of the lower pitches and upper pitches, and it just sort of gives you a very narrow thing. So when you're listening to somebody on the phone, you're listening to somebody with the removed lower frequencies and upper frequencies of their voice, but we can still recognize it. We can still recognize the pitch, if it's a low voice or a high voice. Now, loudness is the perceptual quality that relates to the amplitude of a sound, and it's measured in decibels. And we can measure how people perceive sounds, the loudness of sounds, loud sounds or soft sounds, by using what's called an audibility curve. So we can provide sounds of different pitches at different amplitudes, and see where it is that people can detect sounds and not detect sounds. So here's an example of this amplitude curve, right? Here we have loudness, perceived loudness, and the intensity in decibels. So notice that perceived loudness at a value of 1 relates to decibels 40. Perceived loudness at a value of 2 represents decibels 50. But notice this. Notice that perceived loudness 10 relates to about 70, about 74 decibels, right? So even though we multiplied by 10, going from 1 to 10, we did not multiply by 10 going from 40 to 400. We only went from 40 to 74, which tells you that the higher you go in decibel intensity, it's much louder up here at the top of the decibels than it is down here at the bottom of the decibels. And that's because loudness increases exponentially. It doesn't increase linearly, it's exponential. Notice the scale here on the side. Going on this this chunk of the line here only goes from 0 to 1. And this chunk of the line right here goes from 20 to 100. So that is a huge exponential increase as you go in intensity across from 0 to 100 or 120 on the decibel scale, which tells you again that the perceived loudness up at the very top of the decibel scale is much louder than the perceived loudness down at the bottom of the scale, because it's exponential. It increases in an exponential fashion. Humans hear between 20 and 20 hertz. That's our range of hearing. Of course, other critters are different. So if you're a cetacean like a whale or a dolphin, you can hear much lower frequencies and much higher frequencies. Dogs can hear much higher frequencies, up to 30 kilohertz or 30 kilohertz. We can plot this threshold of hearing in relation to frequency, so we can actually play different frequencies and at different amplitudes, and see what you can hear and what you can't hear. When we do this, most normal humans that have normal hearing have the best hearing between 2,000 and 4,000 hertz, or 2 to 4 kilohertz. And which, of course, is where most voices are. So it's no mistake that our most sensitive hearing is related to our ability to hear voices. So the most voices are between 2 and 4 kilohertz. So it makes sense that our hearing is most sensitive at those ranges. The auditory response area is like the total area where we can perceive sound, and it goes all the way from the lowest level, the lowest frequencies we can hear, all the way to the highest frequency, or the lowest frequencies at the lowest amplitude we can hear, and the highest amplitudes of sound that we can feel. Right, that we can actually feel, where you can feel it in your ears and it hurts your ears. That's our auditory response curve, that range going from the softest to the absolute, where it hurts your ears. So equal loudness curves. One of the things you should understand about sound is that a lot of times higher frequencies sound louder than lower frequencies. Because there's more energy, there's more there's more cycles in there, right? So they sound louder. And so one of the things that is done a lot of times is to see what amplitudes you can adjust to different frequencies so that they sound equally loud. So, for example, I'll take a standard 1,000 hertz tone, which is one of the tones that I played for you earlier on my phone. And then I give you 2 decibel levels. I give you a 40 decibel at 1,000 hertz, 40 decibels, and 1,000 hertz at 80 decibels. So one is soft and one is loud. And then, so that's the standard, right? And then what people do is they hear different tones, and they try to match the tones to that standard. They try to take the tone and match it to the 1,000 hertz standard. What happens when you do these experiments is that pretty much all of the frequencies, all of the tones, at the different hertz are equally loud at about 80 decibels. So it doesn't matter if it's a 1,000 hertz tone or a 3,000 hertz tone. When you play it at 80 decibels, we perceive them as about the same loudness. But that's not true at the lower sound levels. At 40 decibels, they're much softer at 40 decibels. And the ones that sound the softest are the high frequencies and the low frequencies. So it's harder to hear high frequencies and low frequencies at 40 decibels at a lower amplitude than it is to hear the middle frequencies. So it's an interesting effect when it's one of these things that we do to measure the range of things that we can hear with our ears.